Hello everyone. So in the fourth unit, in this session we are going to explain one of the important concept called functions of bounded variation. Functions of bounded variation. See, I have covered maximum syllabus as I already informed in the group that please solve the question papers, but almost all the questions are like abstract. It was not there in the syllabus even though they have asked. So I have collected the notes of Central College as well as BNU, so I have done maximum syllabus. Anyhow, in one of the year you can see the question paper of 2019. Hope so all the 8 questions will be completed. If I do only 1 or 2 videos, but in 2017 last 8th question like Reiser representation theorem and something like Holder's inequality and Minkowski's inequality, all those theorems was not done in any of the universities, but it was asked anyhow. So my suggestion is that please don't neglect 4th unit. So you do copy the 4th unit, please maintain the notes and practice the questions which are there in question paper first, so that it will helpful for you to face the exam. So anyhow, let me explain this concept, and you have a few more theorem based on this concept, and anyhow that is also important as per the point of examination. So function of bounded variation in the sense, suppose if I have a function f which is defined from closed interval ab to a real number r, and almost I have told you that we can divide this into a partition, right? So while explaining 3rd unit I have explained, so I can divide this in terms of partitions. Fine. Then we can define 2 variables, small letter p and small letter n. Small letter p can be defined as I is equal to 1 to m f of xi minus f of xi minus 1. That is positive part of this function. Difference of 2 partition values. So similarly n is defined as I is equal to 1 to m f of xi minus f of xi minus 1 of minus. Fine. Now suppose if you are going to take p minus n, I can write this as I is equal to 1 to m f of xi minus f of xi minus 1. Just a difference in the sense, no need to represent either positive or negative. So we can write the same as f of b minus f of a. So p minus n is given by this inequation. Also p plus n, suppose if you are going to add, I have to write I is equal to n, just a magnitude you are going to write f of xi minus f of xi minus 1. So magnitude value. You have to remember these 2 concepts. Fine. Further, if you are going to represent p plus n, I can write this as t is equal to p plus n. Moreover, p partition from a to b of, p over a interval a to b of a function f is represented by supremum over a function q with reference to p. Similarly, n over b to a. You can note that here a to b. Here also, it is a to b only. So p of a to b of a function f is supremum. So capital N in the sense supremum of q of small n. Remember, as I already defined the function p and n. Fine. So if you are going to take supremum of all the p, we are going to write it as p of a to b of f. Similarly, if you are going to take supremum of n, we are going to represent it as capital N from a to b of a function f. Remember, whenever I have supremum of p over q, I can represent the same as p over a partition a to b of f. Similarly, supremum over all these values of n, I can write this as capital N of a to b of f. So you need to remember these 2 concepts. Further, we can define the function of bounded variation as, suppose if I have a function f from a to b, defined from a comma b to r, is said to be function of bounded variation, and it is represented by f belongs to bounded variation of ab. If each partition variation, if you are going to consider each of the partition inside this part, variation is represented by v of a to b of f and the partition p. That is, function value as well as partition value should be finite. That is, it is less than infinity. Fine. Remember, almost t to a, t of a to b of f is also finite. That is, it should be less than infinity. Fine. And moreover, t from minus infinity to plus infinity of f is represented by limit a to infinity t of b minus a to b of f. Fine. So a function f from a, b to r is said to be function of bounded variation, and it is represented by this if these two conditions satisfies. And moreover, remember p is none other than this and n is none other than this. If you are going to take supremum of p, you are going to represent it with capital P of a to b of f. If you are going to take supremum over n, you are going to represent it with capital N of a to b of f. Fine. And the doubt arises is that what T stands for. T is none other than sum of P of f and N of f. Just now I have written here. Small t is none other than P plus N. Capital T is none other than supremum values of P as well as supremum values of N. So if you are going to add both, you will get T. Fine. So V is none other than variance. That is variation. Clear? And that variance is given by V of A, B of F to P is none other than P plus N. So if you are going to add the value, no, so this sum is none other than V of A, B to F, comma P. I'll just make you the clear. See here, V of A, B over a function F and partition P is none other than P plus N. When you're going to take sum of these two terms, you're going to get variance. And T is none other than, if you're going to take sum, that is capital T. One and the same. Either we can represent variation of f comma p, or we can represent t of f. One and the same. It is representing just the sum of p as well as n. If you are going to take supremum, you are going to represent it with capital P. If you are going to take a supremum of small n, you are going to represent it with capital N. That's all. Everything is same. Further, we have one theorem based on this concept. So just remember this concept, that is basic definition you have to know. P is none other than positive part of a difference of a interval function, and n is none other than negative part of a difference of a function. That is summation of all the values, and p minus n represents the difference value. Moreover, we are not going to represent any sign, and p plus n is none other than variation, or we can represent that as total variation t of a to b of f. And when you are going to take supremum of all the p, it will be capital P, supremum of small n will be capital N. You just remember this statement. So here is the theorem which is based on function of bounded variation, and it is very important theorem as it is asked in many years. So if f is a function defined from a, b to a real number which is a bounded variation, then we have to prove capital T over a interval a to b of function p is equal to capital P plus capital N, and p minus n is equal to f of b minus f of a. Now what I'm going to do is, just to prove this, let me consider a partition, as we already know that we are going to divide this partition inside. So I can divide this partition. So let me take this partition, be the partition required, partitions of AB. What I have done is I have divided the interval AB into n number of partition. Fine. Now we already know that P minus n can be represented by f of B minus f of A. Fine. And it is already explained in the first concept, right? So function of bounded variation, remember P minus n can be represented by f of B minus f of A. It is none other than, it is something like BA, that is AB is an interval. If you are finding the length, we are going to subtract it, right? Like B minus A. So that is why we are representing it by f of B minus f of A. Remember P minus n is equal to f of B minus f of A. So as per the definition, I have considered this. What we say, P minus n can be written as f of B minus f of A. Now I am going to shift n to other side. So you will get n plus, minus shifted to that side, you will get plus n, plus f of B minus f of A. Fine. Now, as you already know that small n is none other than supremum, that is n, capital N of A to B of f. Right? When you are going to take supremum of all the n, supremum for all the values of n, I can write small n as capital N from A to B of f plus f of B minus f of A as it is. Am I clear? Why? Because I just write the reason here. N of A to B of function f is none other than supremum of all the partitions of Q over n. Q is a partition that we have considered, and we are going to take a supremum for all the values of small letter n. You are going to represent it as capital N. So that is why I have replaced n with capital N. Now what I am going to do is I am going to take supremum for LHS value. Taking supremum for LHS over all the partitions of this interval AB, then I can write this as supremum of all the partitions of Q of P is less than or equal to. Remember, when you're going to take supremum, we are going to write less than or equal to. When you're going to take infimum, you're going to write greater than or equal to, as you already know that. So n of A to B of f plus f of B minus f of A. I have rewritten the step as it is. Just the thing is, I have taken supremum for LHS value. Clear? And just I have explained that supremum, whenever you have, see here, supremum of P to P over a partition Q is none other than P over A to B of F. It is one of the representation. If you are going to take supremum over partition P, we can write supremum over all the values of P over the partition Q. We can write that as P from A to B of F. So I can write this as capital P from A to B of F is less than or equal to N from A to B of F plus F of B minus F of A. Am I clear? Now we have arrived just a part for the second equation, right? That is less than or equal to inequality I have. So let me take this as equation 1. Since I have considered it for P minus N, now let me take the reverse, that is N minus P. Now N minus P can be written as reverse, right? F of A minus F of B. See, if P minus N is equal to F of B minus F of A, I can write N minus P as F of A minus F of B. Right? Now similarly I am going to repeat the same procedure. I can extract the value for N. I'll just shift the P. So I can write P plus F of A minus F of B. Similarly, let me take supremum as I done in a previous case. So I can write, when you're going to take a supremum, I can write P over A to B of F is none other than supremum taken over a partition of P. So if you're going to take supremum, I can represent this as capital P from A to B of F plus F of A minus F of B. N is equal to. Now I'm going to take supremum for LHS. Take supremum for LHS. So when you're going to take supremum for LHS value, I can write supremum of N is less than or equal to, as I told you, supremum we are taking, so equals will become less than or equal to plus F of A minus F of B. As I already explained that whenever you have a supremum over N, it is none other than capital N of B to A of F. Here I have a statement, just now I have explained, right? So supremum of small n is none other than capital N from A to B of F, and that is what I have written here, which is less than or equal to P from A to B of F plus F of A minus F of B. So let me take this as equation 2. Fine. So I'll just continue here. And further we know that whenever you have P from A to B is none other than supremum of all the values of P taken over a partition Q, right? So I can write this as which is less than or equal to supremum of P plus N. Meaning is when you're going to take supremum of all the values of P over a partition Q, it is always less than or equal to supremum. It is none other than total variation, right? Why? Because P and N we are taking. P and N is none other than total bounded variation of interval A and B, which is always finite, so it is less than infinity as per the definition. And I have clearly explained that P plus N is none other than total, right? So that is why I have written P plus N as total of interval A to B. And moreover, remember N of A to B is always less than or equal to total. Why? Because as it contains sum of all the P's and sum of all the N's. P is none other than supremum of P is none other than capital P. Supremum of N is none other than capital N. So if you take sum, it is obviously less than T, and it is always less than infinity as it is positive quantity. Right? Now look at the equation 1. I am just going to rewrite the equation 1 from equation 1. See, I'll just write it as P from A to B of F. I'll just shift this statement to here. So I can write minus N of A to B of F is less than or equal to F of B minus F of A. This is from equation 1. Just I have shifted this equation. Now let me consider from equation 2. So here I have an equation 2. Here also I'm going to manipulate. So I'll just shift this. You will get N of A. Equation 2 is here, right? So let me see, N of A to B of F minus P of A to B of F is less than or equal to F of A minus F of B. Now just let me multiply by minus sign. Fine. So I'll just multiply it with negative sign. So this will become minus, this will become plus. So I'll just write it first. P of A to B of F minus N of A to B of F. Similarly, when you're going to multiply it with minus sign, remember inequality gets reversed. So less than will become greater than equal to. So you will get minus sign for this and plus sign for this. So I can write F of B minus F of A. Am I clear? Now look at this equation. Let me take this as equation 4 and equation 5. Clear? Or else let me take this as equation 3. Why? Because equation 2 only taken. So let me take this as equation 3 and equation 4. Now look at equations 3 and 4. So from equations 3 and 4, what we can conclude? See here, one with less than or equal to sign, another with greater than or equal to sign. So from these two equation, result is obvious. We can replace it with equal sign, right? So P from A to B of F minus N from A to B of F will be equal to F of B minus F of A. So this is the required proof of the second one. So I have proved the second one. P of A to B of F minus N of A to B of F will be equal to F of B minus F of A. I have proved the second one. Now let me prove the first inequality, that is T. T of A to B of F is equal to P of A to B of F plus N of A to B of F. So it is very important theorem. You need to practice more. Fine. Now to prove the second one, let me consider the definition. That is, we know that total variation of A to B is none other than supremum of all the partitions of P plus N. Right? We can write T as sum of all the P plus N. See here, T is none other than P, capital P of A to B of F, capital N of A to B of F. Capital P is none other than supremum of small p, plus capital N is none other than supremum of small n. Right? So supremum over partition Q, T over A to B is represented by supremum of P plus N. So that is what I have written here. T over A to B is none other than supremum of P plus N. Right? Now, so from this definition, it is clear that T from A to B of F is always greater than or equal to P plus N. Right? Even though if you are going to take supremum or not, it will be always greater than P plus N. If you are going to take supremum, then also it will be equal. That is when you are going to add both the values. That is supremum of all the values. So if you are going to take individual value, T will be greater as it contains sum of both P and N. Fine. Now let me consider this inequality. So T of A comma B of F is greater than or equal to P. I am going to keep as it is. Now I am going to replace it with N with, see, we know that P minus N is F of B minus F of A as per the definition. Just now I have explained. See here, P minus N is F of B minus F of A. Now I can write this as P. I'll just shift these two terms here. So I can write minus F of B minus F of A. I have just shifted this, which is equal to N. I'm going to shift. You will get N here. So N can be written as P minus F of B minus F of A. So I'll just write N with, see here, I'll just write N with P plus as it is N. I can write N as P minus F of B minus F of A. Clear? As per the definition, I have replaced the value of N. Fine. Now T from A to B of F will be greater than or equal to P plus P is 2P minus F of B minus F of A. This will be true for all the partitions Q. Fine. Now I am going to take supremum of all the values of P. So I can write T from A to B of F will be greater than or equal to, when you are going to take P, small letter P here, so when you are going to take supremum, it will become capital P of A to B minus F of, I'll just write A to B of F minus F of B minus F of A. Fine. Now let me take supremum over all the partitions. So I can write F of B. B is none other than capital P. See, A is always reference to capital N. If you take supremum, B is always reference to capital P. Am I correct? See here, P minus N is none other than, you can remember like this, P minus N is none other than F of B minus F of A. If you are going to take supremum for F of B, it will be equal to P. If you are going to take supremum of F of A, it will be equal to N. So let me take supremum over all the partitions. Taking supremum over all partitions, we can write this as T of A comma B of F will be greater than or equal to 2 times capital B of A to B of F minus, see, when you're going to apply supremum, I have just now explained P of B is none other than capital P. So F of B is none other than capital P of A to B of F. F of A is none other than capital N of A to B of F. Once you have taken supremum, I can write this statement as this. Why? Because F of B is another, B is corresponding to P. So if you're going to take supremum, small b will become capital B. A is corresponding to N. So if you're going to take supremum, it will become capital N. Fine. Now let me take this as equation 5. Look at the equation 5, LHS of equation 5. We can replace this with F of B minus F of A. From equation 5, I'll just replace from equation 5. Look at the equation 5. F of A to B of F minus N of A to B of F is none other than F of B minus F of A. Now I'm going to replace this with F of B minus F of A. We get, see here, LHS as it is, T of A to B of F is greater than or equal to 2 times P from A to B of F minus, see, this term can be replaced by F of B minus F of A. F of B minus F of A. or else we can state this is from equation 5. Right? Why? Because equation 5 states that whenever you have f of b minus f of a, we can write it as p of a to b of f minus n of a to b of f. So I have replaced this term by using equation 5. One and the same. Now let me simplify this. So after simplification, I can write t from a to b of f will be greater than or equal to, see here, 2 times of p from a to b of f minus p from a to b of f. When you subtract, you will get 1 time p from a to b of f. Minus into minus will be plus n of a to b of f. Let me take this as equation 6. But you already know that t from a to b of f is equal to supremum of p plus n, right? So if you're going to take supremum over, as per the definition of total variation of a to b of f is none other than supremum of p plus n. Now let me split this. So as I already told you, when you're going to split the supremum, you have to put equals with less than or equal to. So I can write this as supremum over a partition p plus supremum over n over q. Just I have splitted this supremum, so that is why I have replaced equals with less than or equal to. Now as per the definition, I can write t from a to b of f is less than or equal to, what is the what I can write this as capital P, right? Just now I have explained. See here, p from a to b is none other than supremum of q of p. So I have supremum of p over q. So I can write this as capital P from a to b of f plus similarly this is capital N from a to b of f. Let me take this as equation 7. Now look at the equation 6 and 7. Both the inequality we have arrived. That is one with greater than or equal to and one with less than or equal to. So from equation 6 and 7, we can write they are equal. That is t from a to b of f will be equal to p from a to b of f plus n from a to b of f. Hence the proof. And moreover, it is very important proofs. So it is asked in so many here. Please go through this. So this is the first page. Hope so it is clear for you. As I have applied the definition. So if you understand the definitions properly, whatever I have explained at the beginning of this session, you will come to know this proof. Fine. So here is the one more important theorem. It is also very important as in so many years. So a function of bounded variation is bounded, but converse is not true. So we are going to prove the first statement by the direct proof, whereas for the second, that is for converse part, we are going to use a counter example. Fine. Now let me prove here. Let us consider a function of bounded variation. Let f from a b to a real number or b a function of bounded variation. Fine. So we need to consider a partition. Let me consider a partition AB. So partition of AB will be Q such that we are going to divide the partition, right? So x0 less than x1, so on, less than xn. So last value will be B. So I have divided the partition into n number of I have divided the interval into n number of partition. Let us take an element which is inside this partition. So x be an element which is this inside the interval. So consider the definition of bounded variation, that is f of b minus f of a. So when you're going to take f of b minus f of a, I can write this as summation I is equal to 1 to n. Just now I have explained, right? So see here, f of b minus f of a is none other than p minus n. So it is none other than f of xi minus f of xi minus 1. That is summation. Since you are taking modulus for f of b minus f of a, so you have to take modulus here also. So that is what I am writing here. Modulus of f of xi, I'll just write here. So f of xi minus f of xi minus 1. This is from the definition of function of bounded variation. Since I'm going to split this modulus inside, so equal sign will become less than or equal to summation I is equal to 1 to n f of xi minus f of xi minus 1. Just I have taken this magnitude inside, so that is why equal sign will become less than or equal to. Fine. So this is again from the definition of variation, that is variation from a to b of f. Fine. So definition of variation of a to b of f is none other than f of xi minus. See here, when you have modulus inside of this function, I can write the same as variation of a to b of f. Remember, I'll just give you clarity. See here, suppose if you have f of xi minus f of xi minus 1. So it is just only p minus n. That is summation I is equal to 1 to m. If you have this value, it is p minus n. So if you have magnitude for this, it represents p plus n. P plus n is none other than variance of a to b of f. As per the definition of bounded variation, when you have difference, it represents p minus n. So if you are going to take modulus, for the function which is inside, that is modulus for f of xi minus f of xi minus 1, it represents p plus n. P plus n is none other than variation, total variation of a with reference to b of a function f. So that is why since we have modulus inside, so I can write this as variance of a to b of f. What I have arrived is f of b minus f of a is less than or equal to v from a to b of x. Now let me replace x with b. I am going to replace x with b, so I can get f of x minus f of a will be equal to magnitude of, in the original definition I am going to write. See, f of b minus f of a, this is the definition I have. I have just replaced b with a. So original definition, what it becomes, summation I is equal to 1 to n. Since it is independent of b, so I'll just write in terms of x only. So I have obtained this. Now again I'm going to split the summation, modulus inside, so equals will become less than or equal to summation I is equal to 1 to n magnitude of f of xi minus f of xi minus 1. Again, as I already told you, when you get magnitude inside of the summation, it is none other than total variation. That is variation of a with reference to, here we have variation of a with reference to b, right? So in place of b, what I have? X. So I can write this as variation of a with reference to x of a function fy, because in place of b I have x. Fine. Obviously it will be less than, see here, obviously it will be less than infinity. Why? Because it is positive. And moreover, it is given that function is a bounded variation. That is, f belongs to bounded variation of an interval ab. X is just an element of an interval ab. So this will be what we say, countable. That is finite. It cannot be greater than infinity. That is, infinity is the bounded value for that. So what I have arrived is f of x minus f of a will be less than or equal to variation of a with reference to x of f. X is just an element of an interval ab. Fine. So meaning is, this value is less than this function. The value previous for this is, see, suppose if this is the function, the previous function will be minus f of a. Right? So I'll just write this function. Meaning is, this function will be in between f of a minus variation of a with reference to x less than or equal to f of x minus f of a, which is less than or equal to variation of a with reference to f. Hope so it is clear, right? So, or else I can write the same as, see here, I'll just write one more statement if you are finding difficulty to understand this. See, I can write f of x is less than or equal to variation of a with reference to x. I'll just shift minus f of a to other side, so that you will get plus f of a. Am I correct? And the previous value for this will be minus, right? Variation of a with reference to x of f minus f of a. This will be the previous value. You can clearly note here. See, f of a I have shifted to what we say, right hand side. So I have obtained only this expression. See, previous value for this will be f of a minus v of variation of a with reference to x of f. Meaning is, f of x is a function which is varying between these two values. That is, it is bounded, right? So it is bounded between these two values. Let me take that bounded value as m. So I can write m less than or equal to f of x less than or equal to m. That is, f of x is in between some certain value, right? So I can write this as f of x will be, magnitude of f of x will be less than or equal to m for any values of x which is inside this interval. Meaning is, the function f of x is bounded. So this is the concept of bounded, right? Therefore I can write f is bounded within the interval ab. So we have proved, what we have assumed is, a function is, I have defined a function. What I have proved is f is bounded. Next, what we have to prove is, but the converse is not true. See here, I have assumed a function which is bounded variation. If I have assumed a function which is of bounded variation, so I have arrived that f is bounded. So every bounded function is bounded. That is, every function of bounded variation is bounded. But converse is not true, in the sense, we have to prove, we have to assume one function which is bounded, and we have to show that which is not bounded variation. Don't get confusion. Here I have the function which is of bounded variation. What I have proved is, every function of bounded variation is bounded. Now we have to prove converse is not true. Converse in the sense, if you assume bounded function, it need not be bounded variation. So we have to prove the converse. So converse need not be true. So we can give one counter example for that. So converse is, it is very important, please practice this. Converse is not true. Not true. I'll give an example. For example, let me consider a function f of x as such a way that I'll just consider a step function x into sine pi by x and 0. So this will be only when x not equal to 0, 0 for x is equal to 0. So I have defined one step function such that this is a bounded, right? Clearly, see here f is defined in a domain 0, 1. Why? Because domain for range for sine is 0 and 1 to the real number r. Right? In the sense, meaning is this value, that is sine pi x, will be in between minus 1 and plus 1. As you already familiar with the domain and range in your second PU. So this is the domain for sine, that is minus 1 and plus 1. So we can clearly say that this function is bounded, but we need to prove that this bounded function need not be bounded variance, right? So let me consider the partition of this function. As you already familiar that sine value will be varying from 1 to 0, right? So when you're going to take partition, let me take 2 by 3, 2 by 5, 2 by 7, so on, 2 by 2n minus 1, 2 by 2n plus 1, so on. So I have divided partition in such a way that 1 and 0 have divided in terms of partition. Now let me consider a bounded variation, that is total variation of A with reference to F, A to B with reference to F. So here A value is 1 and B value is 0. Why? Because I have divided the interval 1 to 0. Fine. So as per the definition, I can write I is equal to 1 to n summation f of xi minus f of xi minus 1 as per the definition of total variation of a function. Fine. Now let me put the values as I is equal to 1. So I is equal to 1 stands for 2 by 3. F of 2 by 3 minus f of 1. That meaning is xi plus 1 minus f of xi. Since I have magnitude, so I can interchange this. So lowest value minus greater value. Why? Because in order to avoid the negative sign. Similarly, f of 2 by 5 minus 2 by 3. These two value difference I am going to take f of 2 by 5 minus f of 2 by 3. So if you keep on taking the difference, at certain value you will get f of 0 minus f of last value 2 by 2n plus 1. Clear? Now I'll just write the value f of 2 by 3. 2 by 3 is none other than 2 by 3 only. F of 1 will be 0. Why? Because sine pi will be 0, right? So pi by 1 is 1. 1 into sine pi is 0. So you will not get term for this. Again, f of 2 by 5 is none other than 2 by 5. I'll just keep on adding the values of certain function. Since we have magnitude, so you're going to add all the values of the function. So you will get 2 divided by, for the last value, 2 divided by 2n plus 1. We need to show that this is not convergent. Right? See, this is a bounded function, but we need to prove it is not bounded variation. Bounded variation in the sense it will not be convergent. That is what we need to prove is. So I have added this value. So let me take 4 as a common term. So when you take 4 as a common term, you will get why? Because see here 2 by 3, 2 by 3. You will get 2 times. If you want, I'll just write one more term here, one more step here. 2 by 3 plus 2 by 3 is 2 times of 2 by 3. Plus again you will get somewhere 2 by 5 you will get. So 2 by 3 in 2 by 5 plus 2 by 5 will be 2 times 2 by 5. Right? So on you will get 2 times 2 by 2n plus 1 you will get. So 2 into 2 will be 4. So if you get 4 as common term, you will get 1 by 3 plus 1 by 5 plus 1 by 7 plus so on 1 divided by 2n plus 1. Fine. And clearly the nth sum of these terms, that is n is equal to 1 to infinity 1 divided by 2n plus 1 is a divergent series which is not convergent. Right? Divergent series, or I can say it is not convergent. Clear? So if you take partial sum, nth partial sum of this sequence, this series, is whatever the solution you're going to get, it is not a unique. That is, it is not divergent series. I can say it is not a convergent. Fine. So if it is not convergent, we cannot talk about function of variation. Bounded variation we cannot talk. So I can write variation from 0 to 1 of a function f with reference to p is, that should be finite, right? See here, as we keep on increasing the values, this may not converge into certain value. Anyhow, if you replace n with infinity in the denominator, as per the function of bounded variation, both the denominator and numerator should be finite. But when you substitute n as infinity, the denominator will be infinite. Anyhow, 1 by infinity will be 0, but we are not getting a particular value of a function. So it is obvious. See, when x is equal to 0, then only the function is taking the value 0. So when x is not equal to 0, it cannot be equal to 0, right? But what we are getting is here, when you replace n with infinity, again we are getting it as 0, that is 1 by infinity is 0. So f will not belongs to the variation of an interval 0 and 1. So a bounded function, therefore a bounded function is not function of bounded variation, is not function of bounded variation. So if a function is bounded, it need not be a bounded variation. So if a function is bounded variation, it should be bounded. Clear? As the name itself suggests, bounded variation, in the sense the function should be bounded. But if a function is bounded, it need not be bounded variation. So you have to remember this example. So anyhow, notes will be forwarded in the group. Please copy the same. So here is one more important theorem. It is asked in the year 2019, sixth question, 6th A sub question. Fine. So a proof is 3 to 4 line statements, that's all. So it is asked for only 3 mark, it seems. So a bounded monotonic function on AB is a function of bounded variation on AB. In the sense, a monotonic function which is defined in a closed interval AB is a function of bounded variation. Or they can ask that every monotonic function is a function of bounded variation, one and the same. Remember, every monotonic function is a function of bounded variation. That is also same, and this statement is also same. See here, a bounded monotonic function on AB is a function of bounded variation. That is, a monotonic function which is bounded is a function of bounded variation. Please again don't blame me. I am explaining both the statement in all possible ways. So you just see the video, then you understand properly. So a bounded monotonic function on AB is a function of bounded variation. Fine. Let me prove. So as I already told you, monotonic function, in the sense either we are discussing in terms of increasing sequence or we can discuss in terms of decreasing sequence, right? So let me consider a function which is defined from AB to R, fine, which is bounded and increasing. Either it may be increasing or I can take it as decreasing, one and the same, as it is monotonic. Fine. Decreasing function. It is a sequence of increasing or decreasing function I have defined. Fine. Let me divide this interval into partition. So Q is a partition, as I already taken, it is less than 1. So A is equal to x0, which is less than x1, which is less than x2, so on, which is less than xm. That will be the final value, that is B. I have divided the interval AB into partition as such. So Q is the partition of an interval AB. Now let me define the variation, that is bounded variation of a function f with reference to the partition Q. Suppose if you are taking the partition P, you may get confusion with the definition of function of bounded variation. So that is why I have taken partition as Q. So it is f with respect to Q. So as per the definition, it is summation I is equal to 1 to m, some magnitude of, remember you have to put the magnitude, otherwise it will represent p minus n. I have already told you p plus n representing total variation, so you have to put magnitude here, f of xi minus f of xi minus 1. Clear? Since it is a positive quantity, so again I am going to remove the magnitude. So I can write I is equal to 1 to n f of xi minus f of xi minus 1, because as it contains both increasing and decreasing sequence, so it doesn't matter. So as per the definition, so I can write this as f of b minus f of a. Right? Why? Because n minus p. What is the definition of p minus n? It is f of b minus f of a. So when you don't have magnitude, it is none other than p minus n. P minus n is none other than f of b minus f of a. One and the same. So obviously that will be less than infinity, right? That is function of bounded variation with reference to a to b over a function f with reference to a partition q is less than infinity. So what I have arrived is f variation of a with reference to b of a function f with reference to a partition q is less than infinity. So the function f is satisfying a definition of bounded variation. So I can write f belongs to bounded variation of an interval AB. So what I have assumed is f is bounded increasing and decreasing sequence. In the sense it is a monotonic function. So what I have proved is f is a function of bounded variation. Clear? And that's all. That is the proof. See here, I have assumed that f is a bounded and increasing or decreasing function. In the sense it is the definition of monotonic function. Monotonic function. So what I have proved is f belongs to bounded variation. Therefore f is function of bounded variation. Function of bounded variation. Hence the proof. So here is the next theorem. So this is the second tag question. which is asked in 2019. So just now I have done no. So that question is sixth sub question, first tag question. So this is the second tag question. So it is also very important. So here we are going to prove the function f defined from a b to r is such that f dash exists, in the sense derivative exists and is bounded. So if derivative exists and it is bounded, then we have to prove that f is a function of bounded variation. Fine. So in the previous theorem, it was a function is monotonic, and it is we proved that it is a bounded variation. So in this theorem, we are going to prove a derivative, though. So f dash exists and it is bounded variation. So let me prove. So coming to the proof, similar. So let me define a function from a b to r, and moreover it is differentiable. Let it be differentiable. Differentiable meaning is f dash exists, right? Differentiable meaning is that f dash exists, and moreover let us consider f dash be bounded. So as per the definition of boundedness, you already know that there exists instead of m I am going to take, so just now I have told you, bounded in the sense a function will be in between certain values, right? So instead of m I am going to take k. As per the definition of boundedness of a function, there exists k greater than 0 such that magnitude of f dash of x is less than or equal to k for all x belongs to ab. In the sense, this function f dash of x will be in between, see, any function f of x is bounded, meaning is it will be in between capital and I'm sorry, same value, that is, so I can represent the same as f of x is less than or equal to m. Am I correct? So similarly, since f dash of x is bounded, so I can write f dash of x is less than or equal to k as per the definition of boundedness. Now let me consider a partition q as usual. So we are going to divide this interval into n number of partitions, right? So x0, x1, which is less than x2, so on, which is less than xm, which is equal to b. So it is a partition of an interval ab. Now let me consider a definition of function of bounded variation. It is given by v of a comma b of f with reference to the partition q is none other than summation I is equal to 1 to m. Don't forget to put the absolute value, that is magnitude of f of xi minus f of xi minus 1. So this is as per the definition of function of bounded variation. Fine. Now let me take any element, say ci, that is one of the mean value theorem, right? Intermediate value in between xi minus 1 and xi by mean value theorem. So if I'm going to take that, I can write the same expression as I is equal to 1 to m magnitude of f dash of ci into xi minus 1. So this is as from the concept of mean value theorem. Since ci is one of the value between xi minus 1 and xi, that is one of the value between any two intervals of a partition. So if that was the case, I can rewrite this statement as this. Fine. So meaning is that function of variation from a to b over f of q will always be less than or equal to k times f dash of c is another some constant or bounded value. See here, k is the bounded value into xi minus 1 is none other than length of an interval ab, right? One interval and the value preceding it. So length is always none other than b minus a. So something like that. So it is just a difference value. So I can write this as b minus a. Right? So meaning is that function of bounded variation f belongs to b bounded variation of a comma b, that is f is a function of bounded variation. This implies f is a function of bounded variation. So what we have assumed is if f is differentiable and f dash exists, f dash in the sense differentiation of a function exists and it is bounded. What we have proved is f is a function of bounded variation. So in the theorem 1 we have assumed that f is a function which is bounded, monotonic function which is bounded, and we have proved that it is bounded variation. So in this theorem we have assumed that f dash exists and we have proved that f is a function of bounded variation. Please make sure that these two theorems will be important and it is asked in 2019. It is asked in another form. Please go through the question paper, then you will come to know. So rest of the theorems will be continued in the next session. Thank you.